Welcome to our discussion on exponential functions. The objectives we're going to look at is how to graph them, how to evaluate them, and how to model real-world things with them. So first we need to kind of discuss the basics of what an exponential function is and what its graph looks like. So anything of the form y equals 2 to the x, or in fact y equals a to the x, as we see down here, we can even generalize it more as f of x equals a to the x, as long as a is greater than 0 and not equal to 1. So it can be a fraction, or it can be a number greater than 1, both a whole number or 2.5, things like that. It just can't be 1 itself, because then, of course, if you raise 1 to a power, it's just a constant function. It's just 1, right? And if it's less than 0, it's negative, and that becomes a problem, because as you raise a negative number to an even thing, right, we get a positive answer, but as you raise it to an odd number, we get a negative answer. So that function just bounces back and forth across the x-axis, and it doesn't look anything like an exponential function. So these are the rules that gives us an exponential function. And 2 to the x is just an example of that. If we were to graph something like 10 to the x, 10 being what we call the base of the exponential function, you can see that as we have different powers of x, we're basically just getting different powers of 10, right? 10 to the negative 3 is 1 over 10 cubed, which is 1 over 1,000, so on and so forth, till we get to 10 to the 0, which is 1, and then 10 to the 1, and so on. You can see that regardless of what the base is, right? If the base was 2, 10, 7.5, 1/2, once x equals 0, it will always be 1. So it will always cross through the point 0, 1, because any number raised to the power of 0 always equals 1. So exponential functions of the form c times a to the x, where c is greater than 0 and a is still greater than 1, are called exponential growth functions, because they're used to model growth in diverse applications, business, economics, the sciences, like population growth, biology, if you're looking at growth of bacteria in addition, things like that. Now, obviously, once we start throwing numbers in here, it's going to change the shape, right? These are transformations of functions. And so you could get a function that no longer passes through this point. Now, if we just hit it with a constant, if you haven't learned this, it's the basics of, so here's my basic function. I'm now going to multiply by a constant on the outside. See, this is the outside of the function. When you multiply by a constant on the outside of the function, what that does is it makes it grow faster, so it stretches it vertically. If it was a negative number, it would also flip it vertically, and the thing would the function, instead of growing like this, would get smaller. Okay, so this is what it would look like. It now grows faster, right? We're stretching it, so when x is 0, we get a 1 times c, and now you can see that it no longer goes through 1, it goes through c. So in general, you can think of f of x equals c to the ax always goes through the point 0, c. And then when we go back to the general function where it's just a to the x, c becomes 1, and that's why it goes through the point 0, 1. Here's a simple example. 10,000 is invested at 6% compounded monthly, then the future value of the investment the future value of the investment we will call S after X years is given by this. S equals 10,000 times 1.005 to the 12x. Find the future value of the investment after 5 years and 30 years. Well, all you're doing is you're plugging in 5 for X, and then, of course, 12 times 5 is 60, and then doing the math, and you get 13,488, right? Then you plug in 30, make it 360, do the math, and you get 60,000, rounded to the nearest cent. Note that the amount after 30 years is much more than the amount after 5 years. It's growing faster and faster and faster, and that's what compound interest does. And in fact, compound interest is a form of exponential growth. A special function that occurs frequently in economics and biology is y equals e to the x, or f of x equals e to the x, where e is a fixed irrational number. It's like pi. You know, pi is 3.14159, blah, 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 blah. And it goes on and on and on forever and never repeats. That's an irrational number. E is an irrational number as well. It's 2.71828, blah, 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 blah. It goes on and on and on forever, and the pattern never repeats. Because e is greater than 1, the graph of y equals e to the x will have all the same basic shape as our other normal exponentials. It will go through the point 0, 1, and it will grow rapidly. And to the left, it will, level off and have that horizontal asymptote at y equals 0. Because if you're raising a power, a positive number to a power, it doesn't matter, how negative that number gets. It's always just 1 over that thing to the positive power. So, as e to the 4th, e to the 5th, e to the 6th, those become really, really big numbers. So e to the negative 4th is 1 over e to the 4th, right? E to the negative 100 is 1 over e to the 100. So you're just going to get 1 over increasingly larger and larger numbers, which is why the graph always levels off as you go to negative infinity. It never gets below 0. In fact, it never even reaches 0. Because when you have 1 over a fraction, no matter how big the bottom of that fraction gets, it's never going to equal 0. So if we want to take this e to the x1 and start plotting some values of it, we can get an overall idea of how fast it grows. And in fact, e to the x is used for a special kind of compounding interest called continuous compounding. In the previous example, we had compound interest that was compounded monthly. Here we're going to have continuous compounding, which is the more common compounding in the real world, and it involves using e. Now, in exponential decay functions, those have the exact same form, only your x is negative, right? Your a is greater than 1, or more generally, we can put the c in front of there as well. Make a be greater than 1, c is greater than 0, and now as long as x is negative, we get an exponential decay function, because remember, a negative exponent just means 1 over x, 1 over a to the x. So we get the whole thing kind of flip-flopped. And in fact, when you graph it, you can see that it's just flipped. It's basically spun its way around the y-axis. So instead of rising from left to right, it decreases from left to right. It's literally the mirror image of this function across the y-axis. If you rotated the original one, you would get this function. And that's what multiplying by a negative on the inside of a function does, right? See, this is the inside of the function because it's in here on what's happening. If we put a negative on the outside, it's going to flip over the y-axis, and then you're going to have something that goes down here, like that. We can examine the similarities and the differences between the graphs of f of x equals a to the x and those of mf of x, f of kx, right, x plus h, f of x plus c, and so on and so forth. Basically, what happens when we start transforming these functions? Well, I've already talked about if you multiply on the outside, it's going to make it grow faster if m is bigger than 1. It's going to make it grow slower, right, if m is between 0 and 1. So it either stretches it vertically or compresses it vertically. If you multiply on the inside of the function by a number, it does the same thing as far as stretching and compressing. But because it's on the inside, we describe what it does to the horizontal direction. Everything on the inside of the function affects the horizontal direction. Everything on the outside of the function affects the vertical direction. So if we multiply on the inside of the function by a number bigger than 1, it's still going to do the same thing as multiplying on the outside by 1 bigger than 1. It's going to make it grow faster, which is a vertical stretch. But if you think about, if your function is made out of rubber, if you stretch it vertically, it's going to get thinner. It's going to compress horizontally. So instead of talking about this as being a vertical stretch, we say it's a horizontal compression. And then if the number is a fraction, if it's between 0 and 1, that makes it grow slower, which makes it a horizontal stretch. Right? So these two things actually do the same exact thing. It's just when it's on the outside, we describe its transformation in terms of how it affects the vertical. And when we put it on the inside, we describe its effects as how it affects the horizontal. But it should hopefully be kind of logical if you can just envision, like a balloon. And if you stretch a balloon vertically, it's going to get thinner. And if you stretch a balloon horizontally, it's going to get shorter, right? So a vertical stretch results in a horizontal compression. And a horizontal stretch represents a vertical compression. So they go hand in hand. And that's why it kind of feels like the inside is the opposite, because when you multiply by a big number on the outside, you get a stretch because we're talking about the vertical. When you multiply by a big number on the inside, you get a compression because we're talking about what happens in the horizontal. But it's where you're still getting a vertical stretch, right? So that's where the inside ends up always being the opposite. For instance, if we add a positive number to the outside of a function, it's just going to give every y value is now going to be that much bigger, so everything's going to shift vertically up. Well, if we add something to the inside of the function, it's going to shift horizontally, but in this case, it's going to shift to the left. Because, when we need to get the height, when we originally wanted to get the corresponding height for x equals 3, well, now if we're plugging in, x plus 5, then that height that occurred at 3 needs to happen when we're evaluating 3. But if we're doing x plus 5 and we want to evaluate 3, then x has to be -2, because -2 plus 5 would give us that 3. So you can see that same corresponding height at 3 has now shifted to the left, and it occurs above -2. So instead of being a shift to the right of 5, it's a shift to the left of 5, right? So again, the inside is opposite. This one goes to the left if it's positive, goes to the right if it's negative. This one goes up if it's positive, goes down if it's negative. And those are all the basic shifts and stretches, what we call transformations of functions. It doesn't matter if it's an exponential function or any other kind of function. If you can understand those basic shifts, then you can mess around with any function and know what the graph is going to do once you start doing that, right? So we start with e to the x, we slap a -6 in front of it, it flips it vertically, and it makes it grow faster because of the 6. We start with e to the x, we just slap a 2 in front of it, it doesn't flip, it just makes it grow faster. Okay, so we can see what happens with that. Now, let's model some things. Many types of data can be modeled using exponential functions. There are a lot of things that grow exponentially. Money, right, if you have compound interest, bacteria, populations of anything, people, animals in the wild, all those kinds of things grow exponentially. We noticed that functions of this type have this general form of f of x equals c times a to the x, where a is bigger than 1. And if we're doing decay, then x is just a negative. We still make a greater than 1. Or sometimes we can call it y equals cb to the x, where b is between 0 and 1, which basically just gives us a fraction, right? So remember that a to the negative x is the same thing as a 1 over a to the x. So if we just define b to be a fraction between 0 and 1, and have a positive exponent, it's the same thing. So let me give you some examples so you can wrap your head around it. Let's say our original function was 3 to the negative x. Well, we know by rules of exponents that just equals 1 over 3 to the x, right? But And because this is a 1, it also equals 1/3 the whole thing to the x, because 1 to the x is still 1. And so now you can see that when we're trying to get a decay function, we can really think of it in terms of a regular function with a power of positive x, but the b value has to be between 0 and 1. It has to become a fraction. Okay? So, historically, prices of goods and services rise, resulting in the erosion of the purchasing power of a dollar. With the 2012 dollar as a reference, the 2016 purchasing power is only 0.921, or basically a little over 92 cents, or roughly 92.1% of that value. If we look at a table of what's been happening with purchase power of a 2012 dollar, we can see that it's going down with a measurable rate that ends up being something that we can model. Now, if we use this data with x equaling 0 in 2010, this should be x equals 0 in 2010, to find an exponential function that models the decay of the purchasing power of the 2012 dollar. So what does the model predict as the purchasing power in 2028? And when will the purchasing power fall below 25%? Those are the things we can figure out. So if we plot the points corresponding to the data, we get a scatter plot that looks like this. And it appears to be an exponential decay. It's pretty damn close to linear too, though, right? I mean, you could almost go either way. You would really have to technically run linear regression on it and then run exponential regression on it and see which function fit better, right? Which one had a smaller error rate, and then that would be the better model to use. But in this case, we're going to assume that it fits an exponentially decaying function fairly well, and using technology, we can come up with this function. Here's our c. Here's our a. You'll notice that it's between 0 and 1, which means it's decaying, right? It's getting smaller. And now all we have to do is plug in the values that we want to know. If you wanted to put it in the standard, somewhat standard form, right, where a is greater than 1, then you would just have to do 1 over this to the negative 1 power, which becomes 1.028 when you do this in your calculator to the negative 1, and thus you would turn it into 1.028 to the negative x. I personally prefer not dealing with a negative exponent. I would just do this one. There's really no difference mathematically, so why bother with dealing with a negative exponent? It's just that much more difficult to type into a calculator. Now, remember that we used an unrounded model in our calculations and graphs, unless we're instructed otherwise. So we use 18 for the year 2028, and we evaluate the function. This gives us a purchasing power of about 66 cents. It would make sense to round this to 66 cents. It makes sense to round it to the nearest penny. And then if we want to know when it's going to be below 0.25, we just have to set it equal to that and solve. So we take our original function, and we basically just set it equal to the 25 cents. So 0.25 equals 1.078 times 0.9732 to the x. And now we have to solve for x. So we would divide both sides by 1.078. So we can isolate this part. And we get this. Now, to solve for x, do we just divide both sides by 0.9732? No, because it's not 0.9732 times x. It's 0.9732 raised to the power of x. And you have to know what undoes an exponential, right? What's the inverse of an exponential? The reason why we divide is because it's the inverse of the multiplication that's happening here. So we have to do the inverse of an exponential, which is a logarithm, and the easiest thing to do is just do a natural log of both sides. And what a natural log does is it brings the power down and it becomes x times the natural log of 0.9732. And in fact, this works for any log. You do log base 10, log base 5, log base 7, whatever. It doesn't matter. So you might as well do natural log because we have a natural log button in all of our calculators. And then to solve for x, you divide both sides by that natural log of 0.9732. Now again, you can't cancel natural logs because it's not natural log times something, it's natural log of something. So you'd have to put all this in your calculator to get the answer for x, and once you put it in, you get roughly 53.8. And when you figure out what that is in the model, because knowing that 20, I think it was 2018 was 0. Let me remind myself where it was. 2010, sorry, it was 0. So obviously we add 10 to that. That becomes 54. We add 10 to it, and we get that it happens in the year 2064. All right, that's all I have for you.